mathematicians. In this video, we see a nice CSIR problem asked regarding Galva groups and group action. It's a very simple problem if you know the basic definition of group, Galva group and group action. Let's see. Let G be the Galva group of a field with 9 elements over its subfield with 3 elements. Then the number of orbits for the action of G on the field with 9 element is. Okay, so if you haven't seen the Galva group or the group action, it might look little difficult question, but the definitions are also very simple. Group action is also very simple. So if you know the definition, it is very easy problem. Let's see how to continue. Before this, if you are new to my channel, please subscribe, and if you like my teaching, please click the like button and share with your friends also. If you want me to do some particular topics, you want me to explain some particular topics in mathematics, please use hashtag has Cauchy sequence. Okay, so then I can please comment like that. I will make a video on that. So let's see how to continue this problem. So it's given that G is the Galva group of a field with 9 elements over its subfield with 3 elements. Okay, so if you take Q to be P power n, where P is a prime number and n is any natural number, then you will have a finite field with order Q elements. Okay, every finite field is of order P power n, and given a P power n, there will be a finite field also. Okay, now, so all these things you can find in the finite field section from topics in algebra IN Hestin. Okay, IN Hestin. It's a very nice textbook. Okay. So now, if it is a field, finite field of order P power n, then it has characteristic P. Okay. Again, characteristic is a very important topic for competitive exam. I have made a separate video regarding characteristic of a ring, and the related problems also solved in that video. So please check that. This description of that, I have added the link to that video in the description. Please check. Okay, characteristic. So if Q equal to P power n, then the field FQ has characteristic P. Okay, the prime number P. Therefore, characteristic P means that by definition P times 1 equal to 0. Note that if it is a field, then it will have the it will have 1. Okay, so P dot 1 equal to 0. Now, since P dot 1 equal to 0, if you look at these numbers 1, FQ has, the field has 1. Now you add 1 with itself, 1 plus 1, that is 2. 1 plus 1 plus 1, that is 3. If you keep adding it for P minus 1 times, 1 plus 1 plus 1, etc. 1, that is P minus 1 times. So that this number is P minus 1. This is, so 1, 2, 3 up to P minus 1, all these numbers are in FQ. Because it is a field, so it is closed under addition. So all these numbers up 1, 2, 3 up to P minus 1, all these numbers are here. 0 also there. Now, if you add it for P times, you will get P 1 plus etc. 1 P times, you get P times 1. Right. So, but that is P times 1 is equal to 0. Therefore, you get this 1, 2, etc. P minus 1. If you add 1 more time, you get 0. So, this subset you will get inside FQ. But this is nothing but 1, 2, etc. P minus 1, 0. This is nothing but ZP. You can verify that this is a subfield of FQ. Okay. So this is called a prime subfield. So prime subfield means subfield generated by 1. If it is a finite field of characteristic, if it is a finite field, then it will have a prime characteristic, and in this case you will get the FP as a subfield of FQ. Okay, that is why in the field with 9 elements has a field with 3 elements, because 9 is 3 square. Okay, so that is why it will have characteristic 3. Any field with order 9 characteristic 3, therefore F3 field with 3 elements will be a subfield of that. Now, since if it is a characteristic is of P, then the prime subfield will be FP. But if it is a characteristic of a field is 0, then the prime subfield will be Q, the field of rational numbers. Okay. Okay. So this is our just a basic observation about prime subfield. Now, suppose K is a field containing another field F. This is called field extension. So, what is the definition of Galva group of the field extension? Okay. So, you have to collect all the field automorphism. So, the automorphism K means field automorphism of the field K, such that whichever automorphism fix the elements of the smaller field pointwise. Okay, that is called the Galva group of K over F. Okay, so in this problem we want to find Galva group of F9 over F3. Okay, then this group act on a field with 9 elements, filled with 3 square elements, and we want to count the number of orbits. Okay, so first time if you are seeing this, you might be little tricky, but once you understand it, you can answer all the similar problems very easily. Okay, I will define all the necessary things. Okay, okay. So this is what we want now. Galva group of F3 square over F3. Now let's see what is. So to understand. So this is to okay. Galva group of F3 square over F3 consist of automorphisms of F3 square. Okay, this is 3 square satisfying certain conditions. Okay, so first we have to understand what is automorphism of FQ. Once you know what is automorphism of FQ, then we can take Q to be 9, and inside that automorphism of F9, you can check whichever automorphism satisfies this condition. Okay, so first we want to understand this. So take Q to be P power n, and first I define an automorphism called Frobenius automorphism. So phi from FQ to FQ defined by f of x equal to x power p. Okay, where p is this prime number. Then you can verify that this is indeed a field automorphism from the field FQ to FQ, and not just so this is one automorphism, but all the automorphism of the field FQ, the automorphism group of the field FQ is generated by this automorphism. So if you take so maybe this is should be 5 because I used 5 here. So you take 5 power 0, that is identity automorphism. Then 5 square, you should go up to 5 power n minus 1. Again, where this n minus 1 is this n. Okay, so where this n is equal to this n. Okay, so we conclude that there are n elements here. Okay, and these n elements are generated by this automorphism. Therefore, we conclude that automorphism of FQ is isomorphic to Zn, and the generator is given by the Frobenius automorphism. Okay, if Q equal to P power n, then automorphism of FQ is isomorphic to the cyclic group of order n. Okay, so now we know. So we want to understand this group how this group acts on F3 square, and we want to understand the orbits, number of orbits. So now we know what is art F3 square from our observation. Okay, using this we proceed further. Okay, so okay, let's so this is equal. So okay, now what we have proved is we proved that automorphism of F3 square is isomorphic to Z2. Okay, note that automorphism of F P power n isomorphic to Zn. In our problem, we are given 3 square 9. So it is isomorphic to Z2. So there will be here you will have only 2 automorphism because there are Z2 has 2 elements. So again, first one is identity. Another is you will have pi of x equal to x cube. These are the only 2 automorphism. That is what we just observed here. Okay. Now we have 2 automorphism here, and by definition Galva group of F3 square over F3 is equal to, you have to look at the automorphism of maybe I will change here also F3 square. You have to look at the whichever automorphism here satisfy this condition. Okay, they are all belongs to Galva group. Okay, so but now this set itself has only 2 automorphisms. So we're going to check whether which of these automorphisms fixes the elements of the field F3 pointwise. That is what we're going to check. Okay, so now elements of F3. what are the elements of F3 that we will. So first we claim a more general result. You take any automorphism of the field FQ, then it will fix us the element of the primes of field pointwise. So even if it is a finite characteristic or infinite characteristic, doesn't matter. Any field automorphism of the bigger field will, any field automorphism will fix us the element of the primes of field. Okay, therefore in our case both of these automorphism will fix the elements of the field F3, because F3 is the primes of field of F3 square. That is what we saw. So we get Galva group of F3 square over F3 is nothing but automorphism group of F3 square, because every element of automorphism of F3 square will satisfy this condition. Okay, so let's see why every automorphism of FQ will fix the primes of field. Okay, note that if q equal to p power n, then the primes of field is fp. Now fp is a field with p elements. Okay, so we can assume that this fp is nothing but zp. We know that Zn is a field if and only if n is a prime. So this Zp is also a field with p elements. Any two field of same order are isomorphic. Okay. So elements of the finite field of p elements can be thought of as 0, 1, 2, etc. p minus 1. Okay. Now if it is a field automorphism, definitely it will take 0 to 0, 1 to 1. Now what about 2? F of 2 equal to f of 1 plus 1, which is equal to f of 1 plus f of 1, that is equal to 1 plus 1, 2. Similarly, f of 3 is 3. Similarly, f of p minus 1 equal to p minus 1. Therefore, 0 goes to 0, 1 goes to 1, 2 goes to 2, 3 goes to 3, p minus 1 goes to p minus 1. Therefore, any automorphism of a bigger field fixes the primes of field pointwise. Every element of the primes of field mapped to itself. Okay. Therefore, Galva group of so in general, Galva group of FQ over FP is equal to automorphism of FQ. That is what we have just proved. In particular, in our case, Galva group of F3 square over F3 is isomorphic to automorphism group of F3 square. But automorphism group of F3 square is isomorphic to Z2 and it contains only two automorphisms. One is x goes to x identity, another one is x goes to x cube. Okay, so now we have understood Galva group. Now we want to understand how this Galva group act on F field with 9 elements, and we want to count the number of automorphisms. Okay. Okay. Where is it? Oh. Okay, so here this is fine, this is fine. Okay, so for Galva group of FQ over F3, these two, there are only these two automorphism. So I call them phi 1, phi 2, where phi 1 is the identity automorphism, phi 2 send x2, x cube. Okay, so this is 9, this is 3. Okay, now we want to count the number of orbits. So I take a x belongs to F9. Okay, so what is the definition of orbit of an element? So orbit of an element x equal to, so note that Galva group of F9 over F3, it acts on the field F9. This is the group action we are looking at now. Okay. So yesterday I made a video on group action, basics of group action, and how to find the orbit and how to find the stabilizer. Also we saw the orbit stabilizer theorem also. So I put the link to that video in the description. Please check. Okay. Before continue, better you watch that video so that you know, you will understand what is orbit stabilizer and orbit stabilizer theorem also. Okay. Okay, so by definition, orbit of an element x. So this is a group acting on a set. Okay, so to define an orbit, you have to take an element x belongs to the set. Okay, and the orbit is defined to be on this element x. You have to multiply all the elements of the group G. So pi 1, pi 2 are the only elements of the group. So orbit of x equal to pi 1 of x into phi 2 of x. Okay, so let's see how to use these two count the number of orbits. So not here. Yeah. So if G is a group acting on a set X by orbit stabilizer theorem, G, so we have to fix a X belongs to X, and then we define stabilizer of X to be set of all elements of the group G that fixes X pointwise. Similarly, orbit of X equal to set of all G dot X such that G belongs to G. Please check yesterday video on orbit stabilizer theorem, then this will make better sense to you. Now by orbit stabilizer theorem, we have cardinality of G by cardinality of, sorry, uh, we get cardinality of G by stabilizer of X. This is set of all right cosets of stabilizer of X equal to number of elements in the orbit of X. Okay. So we're going to use this result. Now you take an element belongs to F3. Okay. Then it is stabilizer of X. Stabilizer is set of all elements of G that fixes itself. Okay. But now this G is the automorphism group and this F3 is a prime subfield. Therefore, every element, every automorphism fixes the prime subfield. That is what we just proved. Okay. Therefore, stabilizer of X equal to this pi 1 comma pi 2, this is automorphism of F9. So every automorphism of F9 preserves, maps the point A to itself, right? Therefore its stabilizer will have only one element. Okay, so whatever G you take, sorry, whatever G you take, Gx will be X. Okay, therefore this will be singleton X in case of prime subfield, if the element coming from prime subfield. Okay, therefore therefore since stabilizer has cardinality 2, you can use this orbit stabilizer theorem. So G, the automorphism group that has only two elements. Now stabilizer also has two elements. Therefore, orbit will have 2 by 2. You will have only one element. Okay. So therefore, cardinality of orbit of A equal to 1. In other words, orbit of every element of the prime subfield will be just the element itself. So we got three orbits corresponds to the elements of prime subfield. So now let's take an element A belongs to FQ minus F3. So elements which are not in the prime subfield. So now again we want to understand the stabilizer, whichever, so in the step, so in the group there are only two elements. Okay, again recall that this G, the group G is Galva group of uh, Galva group of F9 over F3, but this we proved it to be equal to automorphism of F9, and this atom of F9 is nothing but pi 1 comma pi 2. Pi 1 is the identity, pi 2 is the x goes to x cube, that automorphism. Okay, now if you want to understand number of elements in the orbit, you have to understand the number of elements in the stabilizer. So stabilizer is set of all elements in the G that fixes the element X. But now in G, this is our G. G has only two elements. So we can explicitly check whether this two elements fixes this element or not. So first phi 1 is an identity element. So identity automorphism. So that will fix every element. So pi 1 of A equal to A for sure. Now what about phi 2 of A? Suppose this element is fixed by phi 2. Okay, note that phi 2 is automorphism x goes to x cube. Okay, so suppose phi 2 of A equal to A, that means that A cube equal to A. This implies A cube minus A equal to 0. This implies A into A square minus 1 equal to 0. This implies A equal to 0, 1 or minus 1. But we are working in the characteristic 3 case. Okay, if characteristic is 3, that means that 3 times 1 equal to 0, or 1 plus 1 equal to 0. This implies 2 equal to minus 1. Okay, so for minus 1 you can replace 2. Therefore, so this phi 2 fixes an element A to A if and only if A equal to 0 or 1 or 2. In other words, so 0, 1 and 2 are the elements of the field F3. So we get a contradiction. So we take an element A outside F3 and you assume that F2 fixes that element, then you get that element belongs to F3. Therefore, the outside F3, if you take element of F9, that element will not fixed by phi 2. Therefore, stabilizer of all the element belongs to here will have only one element. Okay. Now this, by again we come back to orbit stabilization theorem. This has one element. This has two elements. Therefore, this has two elements. Okay. Therefore, if you take any element outside, okay, maybe this is F3, this is F9. Okay, this is F9, this is F3. If you consider, if you take an element here, in this element orbit will be only that, so there will be three elements here. If you take any of these elements, its orbit will have only one element. If you take an element here, its orbit will have two elements. That is what we have proved here. Since stabilizer is just an identity element, its orbit should contain two elements by orbit stabilizer theorem. Now in F3 there are 9 elements. If that element is coming from F3, its orbit will have one element. If you take an element outside F3, that will have two elements. Therefore, one, so all the orbits have either order 1 or 2. So how you can split 9 into sum of 1 and 2? This is the only way. 1 plus 1 plus 1, 2 plus 2 plus 2. Therefore, there are 6 orbits. Okay, so therefore, this is the final answer. Okay. Now, if you have, so I mean, this is requires little bit of work connection with the group action and this orbit stabilization theorem. If you have some doubts, please ask in the comment section. I will help you with this problem. Okay. Also, if you learned something new from this video, please click the like button and share with your friends. Also, subscribe to my channel. Thank you.